Welcome to Developing Graphics Frameworks with Python and OpenGL. Part 37, Textures in OpenGL. In the previous videos, we've spent a lot of time creating a whole bunch of different geometric shapes. Rectangles and boxes, spheres and cylinders, and more. We even created some extra objects like axes and grids to help orient us within a scene, and a movement rig which will help us move around. Starting in this video and continuing on through the next few, you're going to learn how to work with textures, that is, images applied to surfaces to make them look slightly more like real-world objects. For example, here is a box geometry, and a picture, like the side of a wooden crate, has been added to each side of the geometry so that it looks like a wooden crate. So in this series of videos, we're going to learn about, first, in this video, how to create a texture class that allows us to upload images and their pixel data to the GPU. In the next video, we'll learn how to add UV coordinates to geometric objects. And UV coordinates give us a mapping between points on an image and points on a surface. Roughly, it tells us what goes where. Then we'll learn how to use textures within shaders by associating them to uniform variables. And finally, at the end, we'll render a scene using textured objects. The first important concept is a texture object in OpenGL. We will create a texture class in Python, but first we should talk about what it means in OpenGL. Well, a texture object is a data structure, and it stores pixel data from an image in a two-dimensional array of values corresponding to colors. However, it also stores more than that. It also stores information about what algorithms you need to use to determine the colors of a surface the texture is applied to. We might not think about this very often, but usually the size of an image is not going to be exactly the same size as a surface we want to apply it to. We'll typically need to either zoom in or zoom out on the texture and figure out how to associate those values. And the methods or algorithms we use for that process, those are called magnification and minification filters. We'll talk about them a little bit more in a minute. First, let's talk about the beginning, which is going to be to create a texture object. Now, hopefully you remember a little bit about the process of adding vertex data to the GPU. You create a vertex buffer, and we work through a series of references when we're working with that data. It's a very similar process when we're working with textures. First, we need to call the function glGenTextures, and usually we'll just generate one at a time, so texture count will be 1, and that'll give us a reference we can use for a texture object, one that hasn't been used for a texture object yet. Next, we need to use the function glBindTexture. Now, just like working with vertex buffers, we usually don't refer to a texture reference directly. Instead, we bind a texture reference to a specific target, like glTexture2D. And then future OpenGL functions that reference this bind target will in fact reference the referenced target that's been associated. So that will be important to set up, generating a texture and then binding the texture. And then once that's done, we need to use this function glTextImage2D to upload data to the GPU. Now there's a lot of components, a lot of parameters to this function. As we just mentioned, it refers to a bind target. So data will be uploaded to whatever texture reference is currently bound to this target. The parameter corresponding to the data is here. It's pixel data. Now in Python, there's an object called a surface, which is used to store images. Technically, that's in Pygame. But the Pygame library contains a function which can take a surface object, which stores images in Pygame, and convert that to a string buffer, which we can then upload to pixel data. We'll see how that works a little bit later. Some of these parameters, you might guess their meanings, like width and height. That refers to the dimensions of your image. Border refers to how thick your border is around your image, and we're not going to use images with borders, so that will usually be 0. Level is an interesting parameter that won't make too much sense right now. It refers to level in a mipmap, which we'll talk about again a little bit later, but for our purposes, this parameter will also always be 0. Format and internal format tells us what format the pixel data has. For example, some image types, like a JPEG image, only store red, green, and blue values in each pixel. So in that case, the format of that data would be specified by the OpenGL constant, GL_RGB. We'll usually work with, well, we will always work with images that support transparency. This is, for instance, PNG files, portable network graphics. Those are in the format GL_RGBA. And even if we initially load a JPEG image as a texture later on, when we export that data from a Pygame surface, we'll be sure to export it to this format, RGBA. Even if there is no transparency in the image, we'll just uniformly choose to support that. Finally, type tells us about the precision of the color data. Specifically, each one of these values, the RGB and A values, we'll use a byte or 8 bits to store each one. So that will usually be GL unsigned byte. All right. Now we need to talk a little bit about what do we do when the size of an image does not match the size of a surface that it's applied to. Well, there's 2 different cases, and these cases are actually more different than you might expect. The simpler case is when a texture is actually smaller than a surface area. In that case, we'll need to take the texture and scale it up or enlarge it to fit the surface. And that's called magnification. And there's a few different algorithms that are commonly used to figure out which colors in the texture will be used to determine the colors of a fragment. One of these is called nearest neighbor filtering. And the idea for this is that given a point on the surface, calculate the closest point on the texture and just use the color of that point for the point on the surface. So it basically enlarges the texture, but it's going to cause a very blocky or pixelated appearance. There's no smoothing that goes on with this approach. So it's not used too often. More commonly used for magnification is linear, or sometimes called bilinear filtering. The idea behind this algorithm is for any point on the surface, it calculates the 4 closest points on the texture and then calculates a weighted average of those points. And this causes the color to be smoothed as it's enlarged. The other case we have to worry about is when we're applying texture data, what happens if the texture is larger than the surface? Well, then we need to scale down the texture. We need to make the texture smaller. And this process, the opposite of magnification, is called minification. And this case is surprisingly significantly more complex. And here's why. When you shrink a texture, then the points in the texture will be smaller than the points on the fragment. So you'll have many texture points which are going to correspond to each point in the fragment. Now, which algorithm should you use? You could use the nearest neighbor algorithm, right? Again, for each point on the fragment, choose the closest point in the texture. There will be lots of such points, but choose one, but that's actually going to create some unwanted visual artifacts. Another choice could be to use linear filtering. But again, if you're really scaling down that texture a lot, there might be, dozens or maybe even hundreds of points on a texture that correspond to a particular fragment. And doing a weighted average of hundreds of points is really inefficient. So a technique which is often used for minification is called MIP mapping. And the idea is this. When you upload a texture to the GPU, such as this crate texture shown right here, you can ask the GPU to calculate a MIP map. A MIP map is a sequence of images, and in each image in the sequence, the width and the height are half the size of the previous image. So starting with our original image, maybe this is 128 by 128 pixels, then 64 by 64, 32 by 32, all the way down to a single pixel. And then, when you want to use minification, one of the algorithms could be to choose the image in the MIP-map sequence which is closest in size to your surface, and then just do linear filtering on that. That brings us to some more OpenGL functions. So if you want to use MIP mapping, which we will, you would use the OpenGL function gl generate mipmap. And then this will only work if you've already uploaded some pixel data to the GPU, so be sure to do that first. But whatever texture is currently bound to this target, the GPU will generate and store that sequence of mipmap images, and then use them if needed. There's another function called gl text parameter I for integer, and this is an interesting function. It's a very general purpose function, and you can use it to set the value of a named parameter in OpenGL. Two that we should always set are what algorithms we'll use for magnification and minification. So some possible values for a parameter name would be these OpenGL constants, which correspond to the magnification and minification algorithm. To set those values, you could use parameter values like these. So for example, if you want to use the nearest neighbor algorithm when minifying or magnifying, you would use gl nearest as your parameter value. If you want to use linear filtering, again, you could use that. If you choose to use MIP mapping, there's a lot of different constants which you could use. This constant, this parameter value, only really makes sense in terms of minification. This describes the algorithm we mentioned on the previous slide. When minifying, choose the MIP map nearest in size, and then you could do linear interpolation of the 4 closest texels. And there's lots of other choices you could use as well, but those are some of them. And finally, there's one more thing we'll use this general purpose OpenGL function for, and that's to determine how to wrap a texture. Now what we mean by that is that typically texture coordinates range between 0 and 1. Right? But it is possible that the UV coordinates might be outside of that range. So what should the GPU do if it encounters UV coordinates like 1.5, 1.5? Right? There's a couple of different behaviors you could use. For example, once you go from 0 to 1, you could just go back to 0 and repeat the UV values. Sometimes you could think of that as taking the fractional part of a number or reducing the number modulo 1. But that process is called repeating the texture. So here in this image on the left, I have one base texture, which is repeated total of 3 times in each direction. You can kind of see if you look closely that those images do not line up. There are obvious seams in this texture. That's one possibility. The next possibility, if UV coordinates go outside the range 0 to 1, you could just clamp them to the nearest value. That is to say, UV coordinates greater than 1 become 1. UV coordinates less than 0 become 0. It's called clamping to the edge, and that would result in a texture like this. Right, so 0, 0 would be this point on the lower left. 1, 1 would be this point on the upper right. And then once you go beyond that region, all these color values correspond to the right edge here. All the color values on the left correspond to the left edge here. And similarly for the top and the bottom. That'd be clamp to edge. And there's also something called clamp to border. You can actually specify a border color, and then anything outside that range automatically becomes that border color. So in this case, the border color is just a dark gray. So those are some more uses of this function here. And with all that information, all those OpenGL functions at our disposal, it's time to write the texture class. So we're going to return to our graphics framework. And this is a really important class. So we're going to go ahead and put a new file in the core directory. So in Sublime Text, I'm going to right-click on core and create a new file. And I'll immediately save it. This is going to be called texture.py. texture.py. All right, we're going to need to import the Pygame library because that has a function for loading image files from our directory. And it also has a function that will convert the data stored in a surface to a format we can upload to the GPU. So we'll import that. And we're also going to be using all those OpenGL functions we just talked about. So from OpenGL.gl, we'll import all the different functions and constants. All right, let's make a class called texture. Oh, the class is called texture. Extending the base object class. And let's create the init function. By default, we'll have some kind of a file name. And this will actually be an optional parameter. Sometimes you might want to generate a surface directly rather than load it from an image file. So this will be an optional parameter. Additionally, I'm going to include a parameter called properties, a dictionary that will be empty by default, but properties would be where you can set different values for the default properties that are used when uploading an image. So for example, changing the wrap behavior of the texture, what happens to UV coordinates outside the base range, or choosing the magnification and minification functions. You can specify all that with properties, or just accept the default values, which we're going to set up. All right, so first we need a Pygame surface object to store the image data. It's very convenient that this exists. Initially, it will be none until we load it. And now let's generate a texture reference. And so we'll store that as texture ref. We'll get that with GL gen textures. And let's also set our default property values. That is the 3 things that we can customize with the GL tech parameter function we just learned about. So the properties by default, let's call them mag filter. And this will be, we'll use linear by default. Provides a nice smooth appearance. The minification filter. For that one, let's use GL linear mipmap linear. This allows you to use the 2 closest mipmaps and linear interpolate a color between those two close maps, and then linearly interpolate the results. It's a good minification filter. And then finally, for wrapping, by default, we'll just use repeating texture. All right, so those will be the default properties that we're going to use. And you might want to overwrite these default properties. So we'll add that functionality with the function in just a moment. So to overwrite the default property values, pretty soon we'll write a function called setProperties. And then if a file name has been given, so if file name is not none, there's something there, we're going to write another function called loadImage, load an image from this file. And once we've loaded it, we will upload data to the GPU. Okay, that's the init function. Now let's write some of these helper functions that we indirectly referenced here. So first, to load image data from a file, this will be called loadImage. Takes a file name as a parameter. Then it's as easy as you could hope. From the Pygrain library, the image class, we're going to load that file name. That's that. Next, function to set property values. We'll only use this if you want something different than the default, which is possible. We'll call this setProperties. All right, so properties is a dictionary, and I'd like to iterate over both the keys and the values. I'll call those variables name and data. So I want to make sure that I'm setting a property that actually exists. So if name is in self.properties.keys, then we can change the value. Self.properties at the index given by the name, let's set it to whatever that value is. Else, this is where we do the error checking. We'll raise an exception, no property named plus whatever the name is. All right, that's it for set properties. Now, let's do the big function. Now, this is the last function we need, but it's by far the longest. It's going to be where we upload the data. So upload pixel data to the GPU. And the reason it's so long is that function which uploads data has so many parameters to set. So let's call this upload data. We don't need to pass it any information because we assume the surface has already been set up. So we're going to store image dimensions first. And we can actually retrieve those, again, with Pygain functions. Self.surface.get_width. And the height, self.surface.get_height. All right, so next we're going to convert image to a string buffer to upload. We'll call that pixel data equals Pygain image to string self.surface. And we can specify how we want the data, so we'll just always specify that we want RGBA data. And so this will add transparency information even if we load it in an image file that doesn't have it. And the one is just an extra parameter. All right, time to bind the texture. And so we do that with, appropriately enough, GL bind texture. we're always going to bind to GL texture 2D. There are actually one-dimensional and three-dimensional textures, but we won't use them here. We also need that texture reference we just generated. And now we activate the big function, right? Send the data to the texture object. All right, so this function is GL text image 2D. We have to give it the bind target. It's GL texture 2D. 0, the internal format that's going to store it as RGBA data. Then we need to give it width and height. The first 0 is level, the second 0 is border maybe. And then we're using 8-bit images, so unsigned byte. And last but not least, the pixel data. All right, still not done though. Once we've uploaded that data, we need to generate our mipmaps. So that's created with GL generate mipmap. Again, for whatever is bound to GL texture 2D. And then we need to use our GL text parameter. So we're going to set texture parameters next. The first one, let's see, GL text parameter I, GL texture 2D, GL texture, the magnification filter, and we're going to use, well, whatever's in properties. Right, so that's stored, the OpenGL constant is stored in self.properties under the key mag filter. All right, and then I'm going to copy paste this because the min filter, that command is only slightly different. Change mag to min, and here change mag to min as well. And then we need to set up our texture wrap parameter. So again, GL tech parameter I, GL texture 2D. In this case, GL texture wrap S. It's actually an interesting thing. Why do they use S and T rather than U and V? Let's say conventions, and leave it at that. But you can think of texture wrap S as the U of the UV coordinate. Self properties, wrap. And then the second texture coordinate is texture wrap T. All right, so that's all we need for the texture class. Unfortunately, we're not really at a point where we can test this out yet. We still need to add some more data and classes to our framework. But this is a good start. We've learned a little bit about textures. The next step is going to be to go back and visit some of our different classes for geometry objects and add UV coordinate data to each of those. Thanks for watching.